Good morning and welcome back. This is still the rather extended discussion of amphibians in the Gulf of Guinea in Africa. And I now realize that we've got two more vignettes to get to the end, although I really like this case study because what it's doing, in my opinion, is it's focusing on a puzzle. It's a biological puzzle of great interest with all sorts of different pieces. There is an overall evolutionary puzzle, which evolution could be called biology's greatest idea. There is a more specific sort of ecological and biogeographical element, which has to do with how it is in space and time that living organisms have colonized different parts of the Earth. Very, very cool. And amphibians on oceanic islands is just a really neat example of this. Then that put lots of demands on us at the level of, let's say, physiology and trying to understand something that we take so incredibly for granted. Namely, I'm looking here. Maybe I shaved yesterday. I've got this stuff here. I'm touching. It's called skin. But you could grab a piece of the skin. You could go to Whole Foods, buy a whole chicken, and take the skin with the knife and pull it off, and you could in principle make a measurement of how well various molecules get across that skin. And so there's a whole physics story about that, and that pertains to drying out of frogs when they're put in salt water. Now that's a vast oversimplification, so I'm using this really as a toy in order for us to explore many important ideas. We've talked now in detail about entropy, and I'm going to assume that I can refer to entropy at will from here on in. We've talked about osmotic pressure. We've talked about the second law of thermodynamics, which is to say that systems will tend towards an entropy maximum. Of course, the whole story of biology in some ways, that's a little hyperbole, is to defy that. So I am not in equilibrium. Napoleon is in equilibrium. And so the defiance is really going to be one of the main threads of everything else that we're going to talk about. So what I want to do here is this vignette, this one right now, is still in the sort of spirit of introducing the relevant physicochemical insights and laws and calculations. So today we're going to talk about the linear transport laws. And then the next vignette and the final vignette on this section is the calculation of how long to dry the frog out. So that's really the denouement of this whole long exercise. And it will leave us with I guess I could say a hypothesis, which is some sort of a sense that in an extremely rainy year, the Gulf of Guinea might become sufficiently brackish, that is to say low enough salt concentration, that frogs could float on a log or something without drying out and make the journey. There's so many things that I don't understand about this, and probably no one does, about how to reckon and deal with these extremely improbable events. That's for another day. Okay, so with that as the background, I want to start out with the subject of dynamics versus equilibrium. So we earlier introduced the second law in sort of this very sterile but very powerful fashion. Sterile in the sense that all reference to real world situations has been abstracted away, and we're left with this very simple notion of two reservoirs that have different numbers of molecules, which are shown in red, separated by a membrane, and that membrane is permeable to water, for example, or to the red molecules, for example. And what we're going to ask is what happens to the entropy. Equilibrium is the concept that there's a terminal privileged state, and that terminal privileged state is a superlative state in the mathematical sense because the entropy is maximized, as shown as at the peak in the green curve. What I'm saying is that if we start out over on the left side of this graph, which is 0 particles on the left-hand side, then there's no entropy associated with the left-hand side. There's lots of entropy associated with the particles on the right-hand side. And now what will happen is that particles will start moving from right to left, and the entropy on the left side will start to go up, and the entropy on the right-hand side will start to go down, and those will compensate each other, and at some point, the mass transport will stop because the entropy is maximized. So now, when I talk about dynamics versus equilibrium, in its bare form, the second law of thermodynamics is really a statement about the final state. It's not a statement about the dynamics. What we're going to do now is we're going to say, well, we can think about the trajectory as those particles move across that membrane, and that's the dynamics. That's the thing that's going to tell us about the approach to equilibrium. And what we're going to do now is we're going to introduce a special category of transport laws, which is limited in scope, but nevertheless very powerful. And these are the great classic linear transport laws, many of which you're familiar with. They have names, which I remind you of on the right-hand side. So maybe the most familiar of them, one that somehow gets ruined, at least for me, kind of because of a classic high school physics plug and chug philosophy. It's 3 laws. I'm kidding around, but there's law number 1 is current is equal to voltage divided by resistance, and law number 2 is voltage is current times resistance, etc. But it leaves a very bad taste in my mouth, and that's bad because when I was a kid, my mom and dad were really very willing to spend money in the name of kind of my interest in the history of science, and so I might even have one of the books nearby, but I got a really cool copy of Gauss's treatise on differential geometry, or William Rowan Hamilton's book on quaternions, or Laplace's celestial mechanics, and one of the other books that I got was Ohm's book, in which he discovered this stuff, which was incredibly profound. And the irritation that I feel is like this becomes like a trivial thing. Oh, you tell somebody there's a certain resistor and there's a certain voltage and compute the current. It's just like completely mind-numbing nonsense. It's not conceptual. So here, I'm at least trying to put Ohm's law into the context of, oh wow, there's an electric flux, and the driving force of that is the electric field, and there's a linear relationship between those two things. Flux being number of charges per area per time, and driving force is the electric field, and this coefficient, which is actually, interestingly, in general, a tensor. I'm not going to talk about that yet, but we will indeed talk about tensors later. It ends up being converted from this highly trivial plug and chug, prepare for MCAT nonsense to a profound example of a linear transport law. The second example is the Ficks law, which we'll come back to quite a bit in the next few weeks. It's the phenomenological law that presides over mass transport in diffusion. And what it says is that if I have this box, on one side there's more molecules than the other, it says that the flux, and I want to, let's be serious here. So let's talk about Fick's law, and note over here on the right-hand side in particular. So the first thing I want to say is let's really, really absorb in our hearts, our minds, our spirit, that we need to know what the units of these things are. So flux of matter is number of molecules per area per time. So, it could be blah, blah. It could be 50 molecules per centimeter squared per second, or it could be 51 molecule per nanometer squared per second, or 1 ion per micron squared per second, which might be, a number for permeability of a lipid bilayer membrane. So that's the left-hand side. We know the units are number of molecules per area per time, and just, to look at a different example, here I show you the flux of heat, in this case. There, the flux has units of energy per area per time. Always the denominator is going to be per area per time, but the numerator could be different. The one we're going to be interested in now is this one, flux of water. And note that the units are cubic centimeters per square centimeters per time, or volume per area per time. I love that because it's weird because the natural intuitive units are volume per area per time, but when you write that down, what you get is a length per time, and that can be confusing. So anyway, to come back to Fick's law, just to make sure that we're kind of on board with it, there's a linear relationship between flux on the one hand and the driving force, which is the gradient in the concentration. So what I hope you see in the middle graph is that, I show you several profiles of concentration as a function of position. So I'm moving from left to right, and I look and I notice that the concentration goes up as I move to the right. That's cool. I show you two scenarios. One is in which there's a shallow gradient, the other of which has a steeper gradient. And we note, or we intuit, we guess that there will be a higher flux from right to left in the case where the gradient is steeper. And so that's what this dc by dx is measuring. And then in all of these cases, there's a transport coefficient. So again, to organize, we're interested in a flux. There's a corresponding driving force, and then there's a coefficient that relates those two quantities linearly. So diffusion coefficient relates flux to concentration gradient. The thermal conductivity relates thermal flux to temperature gradient. The viscosity relates flux of momentum to velocity gradient. And the permeability coefficient, shown here, relates the water flux to the concentration gradient, where really the driver here is the osmotic pressure. So, or said differently, the concentration gradient of the objects that are not able to get across the membrane. So let's just remind ourselves of what we're really thinking of in this case. We've got molecules on the two sides, and they do not get to cross the membrane, but the water does. And so what happens is that, water is going to move from one side to the other in order to dilute the higher concentration stuff. And that brings us back to the way we're going to think about mass transport in the context of the frog. So, so to summarize, in the case of diffusion, which again we're going to spend time on next week, what we see is that there's this beautiful, simple linear relationship called Fick's law. And now what I want to do is I want to specialize to the case of the linear transport law having to do with water transport. And this is just by way of introduction. It's just pointing out to you that people do clever experiments. You can go grab this paper. PLOS journals are freely available online. Just take the title. Why amphibians are more sensitive than mammals to xenobiotics. This is a significant study because people are very interested in extinctions that seem to be going on, and the rate of amphibian extinction seems to be higher than the background rate. And so people have been wondering what's special, what's interesting, what's different in the context of amphibians. And the thing I guess the reason I wanted to point this paper out to you was just to say, there's a device. I mentioned Whole Foods, and here's what the device does. You could imagine, here's an old school way of thinking about it. I could have a membrane, which is the skin, and on one side I could have water that's radioactive, and on the other side I could have water that's not radioactive initially at t equals 0. And then I start my stopwatch, and then what I do is I measure the amount of accumulated radioactivity on the side that originally had no radioactivity. And I know the area of the membrane, and I know the initial concentration gradient, and then I measure the flux, basically. And from that, one can determine the coefficient, the permeability of that skin. And what I want you to notice here is that these are experiments done on both pig skin and on frog skin. That's interesting. And the key point for my purposes, and really where we're going to stop this vignette, is to note that the x-axis is different for the frog and the pig ear skin. Note, on the top, the permeability, centimeters per hour, for the pig skin, has got this low value of 0.2. And then on the bottom, the units are still centimeters per hour, but the numbers are, 10 to 50 to 100, 100-fold or something bigger. So the point being that the skin of the amphibian is much more permeable than would be our skin or that of a pig. And so the hypothesis is that the higher permeability of the amphibian skin gives rise to a willingness of the skin to take on board these environmental insults that all of us are subjected to. In fact, I notice even this morning as I was brushing my teeth that there's a taste in the water that I can tell is related to things that are in the pipes and stuff. And I've never liked that. I've always noticed that. And, the problem is invisibility. I mentioned, I talked about it in the evolution class that's also on parts of which are online, that Claire Patterson at Caltech, was trying to measure the age of the Earth, and that was based on uranium-lead decay, and dating was based on measuring the amount of lead in rocks, and basically he realized that there was contamination in his glass and paint and just like water, everything around him, and consecrated much of his career then to dealing with that question, the environmental impacts of lead and trying to mitigate it. And the only reason I bring it up is just, again, it's the weirdness of invisibility. So many things are invisible to us, and yet that doesn't make them any less real. Yeah, pandemic is a very good example of that. There's a kilogram of SARS-CoV-2 virus, currently wandering around on this planet, wreaking absolute havoc. So anyway, okay, what have we accomplished in this vignette? So just to recapitulate the key points that I wanted to get across, I really wanted to note that if a system is not in equilibrium yet, the second law is demanding it go towards equilibrium. And what I'm telling you is there's a set of linear phenomenological laws that tell us about the way that the entropy will increase. How? Because there will be fluxes. The fluxes are described by a simple relationship, a simple linear relationship between flux, which is stuff per area per time, is linearly related to degree of disequilibrium. Degree of disequilibrium, or driving force, is measured usually by gradients. So the electric field is actually, some of you might remember, is dV by dx, just for example, if I'm doing a one-dimensional thing. So that's the degree of disequilibrium of the voltage. The degree of disequilibrium of a concentration field is that there's a concentration gradient. If I have a non-uniform temperature distribution, that is a driving force for heat flow. All of these correspond, though, fundamentally to the system moving towards the state of equilibrium. Note, a cell has like 100 millimolar concentration gradient of potassium across the membrane. That thing is maintained. It's a battery, and it's maintained by pumps. So energy needs to be consumed to defy the strictures of the second law of thermodynamics. In the absence of that driving force, what happens is the return to equilibrium, and it is manifested, at least for small degree of disequilibrium, for small gradients, by these linear transport laws. My big complaint is the physics of non-equilibrium is not sufficiently in hand, in my opinion, to handle the broad sweep of living matter. We have more work to do to go beyond these linear transport laws. So I talked about the linear transport law, and I leave you with the idea that there's this simple relationship between flux of water and the concentration gradient of some osmolyte, which cannot get across the semi-permeable membrane, and which drives the flow of water again, because of the second law of thermodynamics, because the entropy of the osmolytes will, on the side where there's more of them, will be increased if more water goes over there. So with respect to the frog is going to deliver some of its water to the ocean in order to dilute the ocean so that the ocean's entropy goes up. That's my vague and sort of intuitive description of what's going on in these problems. So I think that that's what I want to say up till now. And so the final vignette on this stuff will be about the actual drying out time.